Hello, everyone. Welcome to today's deep dive. My name is Thomas Thompson. I'm a co founder at Eduade AI, and today we will look at worked examples. Helping students master new concepts means juggling multiple cognitive demands, lesson objectives, scaffolding, engagement, assessment, all at once. Worked examples are a tool to help us with this juggling act. Grounded in solid research from cognitive science, they provide teachers with a structured, step by step way to introduce new skills, reduce cognitive overload, and guide students toward independent problem solving. So, what's a worked example anyway? Worked examples are step by step illustrations or demonstrations that show learners exactly how to solve a specific problem or complete a task rather than having students flounder with trial and error or inquiry based learning first and from the start where they may form persistent misconceptions. They get to see what an expert, you or another model, would do. They're most powerful for novice learners or those approaching a wholly novel or new skill or problem. You should think of it like showing someone how to complete a recipe before having them cook that recipe independently. Once they see how all the ingredients come together, they can apply that knowledge in their own kitchen. However, if you were to sit Marco Pierre White down and show him how to prepare a bolognese, that would likely not be a good use of anyone's time because, well, Marco Pierre White is already a master at making a bolognese. He doesn't need a step by step demonstration from someone less advanced than him. I've linked a blog post down below with much more details on worked examples. Feel free to check it out if you're interested in some of the key research findings or some of the practical classroom applications. But now let's look at Eduate and how our worked example tool bridges research and practice. You can find worked examples under the information objects category. It's right here. It's one of our popular tools, but it's also under the conceptual tools subgroup, along with acronyms and elaborated analogies. I'm going to show you some examples from a math class that will be dividing multi digit numbers. That's middle school. Then we'll look at a high school chemistry course looking at chemical equations. And finally, we'll calculate nominal GDP for an intro to economics course. So I have my multi digit division using the standard algorithm. That's the standards based text, which you can pull up here using our standard search tool. Just math standards. It's already mapped to middle school. That's our grade that we have selected. And you can look those up, and it's right here. I already hit add to workspace, and we have our worked example here. Let's look at its parts and break it down piece by piece. Let's go to focus mode. Let's go full screen. Let's zoom in a bit, and here we go. You begin with a learning objective. Students will learn to fluently divide multi-digit numbers using the standard algorithm. The target audience, again, middle school, grades 6 to 8, and a little hint to the background knowledge, they should have knowledge of basic division concepts. Here's our problem statement. 144 divided by 12. And now Eduade provides what do we have here? A 5-step solution. Let's work through those steps. You set up the long division. We're writing 12 outside the division bracket with 144 inside it. We determine how many times 12 fits into the first digit of 144. 12 does not fit into 1, so we look at the first two digits, 14. Well, we know that 12 fits into 14 one time. We explain that we write 1 above the division bracket, we multiply 12 by 1 and subtract from 14. Subtract 12 from 14 to find the remainder is step 3 here. Step 4, determine how many times 12 fits into 24. We write 2 above the division bracket next to 1, multiply by 12 by 2, and subtract from 24. Subtract 24 from 24, find the remainder. The remainder is 0, and this indicates that for 144, it's evenly divisible by 12. Now, I didn't do a great job of explaining it. I'm not a math teacher, but for all the math teachers out there, I think you get a sense. Step 1, step 2, step 3, step 4, step 5, we break down how to actually find the how many times 144 is divisible by 12. So then we should move into broader guidance outside of just a 144 divided by 12 type thing here. We can move into self-explanation prompts. Why do we look at 2 digits instead of 1 when dividing 144 by 12? We could also do some fading guidance where we provide a similar problem with the first two steps completed, like 252 divided by 14, then prompt students to complete the final steps independently. We can identify common mistakes students may make, ask students, what is the error in this reasoning? How would you correct it? And then opening up to practice problems for themselves. 225 divided by 15, 360 divided by 18, 489 divided by 21. We have our feedback mechanisms built in here. 225 divided by 15 is 15, 360 divided by 18 is 20, 489 divided by 21 is like 23 point something, something, something. Then you want to connect to your prior knowledge, right? This method uses the same long division techniques previously learned with single digit divisors because we can assume that students worked with single digit divisors before moving on to the multi digit numbers here. And then finally, extend to new contexts. So that's a worked example for a middle school math class. But what happens if we're doing, oh, I don't know, ninth to 10th grade chemistry and we're looking at, I don't know, refine the design of a chemical system by specifying a change in conditions that would produce increased amounts of products at equilibrium? That's a next generation science standard. Let's take that. We see it generating. We have our learning objective. We have our target audience with some of the background knowledge noted. We have the chemical equation, the equilibrium reaction here. We have our step by step solutions. So we identify the current conditions of equilibrium. We consider the effect of changing concentration. We analyze the effect of pressure changes. We evaluate the impact of temperature changes. So what should we do? Well, we have an optional, you should add a visual diagram illustrating the shift in equilibrium with arrows showing the shift towards products when reactants are added and when pressure is increased. Some self-explanation prompting. And then, of course, partially worked examples for later practice. We give an example like this. We complete steps 1 and 2. We have the students finish it. We have some your turn problems. And every once in a while, you might see the AI kind of screw up the formatting here. That may occur. You can always hit add to workspace again. You could fill in your own problem, but generally, it will nail the proper chemical reactions here. Okay. And now let's go look at our last example, which will go to 11th, 12th grade. Let's set it for what calculating nominal GDP. Add to workspace. Oh, here we go. Consumption, investment, government spending, exports, imports. We identify the components. We plug in the values. We calculate the next net exports. We sum all the components. And we learn the basics of the nominal GDP calculation. Some fading guidance, error identification, your turn problems, calculate the nominal GDP for the following. We provide the consumption, investment, government spending, exports, imports, everything you need to do it. Connect to prior knowledge, extend in new contexts. And here is where we see the same type of worked example across an arbitrary number of generations, kind of reliability. So, in short, you want a step by step solution. Try to insert maybe some self explanation prompts, some guiding questions, fading guidance for scaffolding. This allows teachers to provide partially completed examples, error identification tasks with maybe incorrect worked examples for students to analyze, and then you integrate it with practice and feedback. So here's the best practices. Start small. Use short, straightforward examples to introduce the format before moving into more complex problems. 2. Model self explanation. Demonstrate how to articulate reasoning aloud. 3. Gradually remove support. Use fading guidance to transition students from structured examples to independent problem solving. Incorporate error analysis, present common mistakes, and ask students to identify and correct them. And then encourage reflection. Have students revisit worked examples after completing problems to reinforce learning. So don't forget to like and subscribe. Get more at the intersection of education, AI, and cognitive science. I hope you found these worked examples interesting, maybe useful. Thank you.